few minutes early, so we will here. Okay, I'm sorry.
Is that the only 5 comments available?
Okay, my name is Ren Fu Guo. I'm from Zhongzhen University. And I will be the chair for this session. As a reminder,
But they are now asking a question about it. This is only 5
Yes.
topics available now.
as a reminder, you have to turn off your electronics. Recording is prohibited for this entire session. Okay. Now I would like to ask jurors to introduce themselves. Let's start here.
So my name is Xu Hongwei. I'm from National Synchrotron Radiation Research Center. So
I'm Yang Xiaowei from National University.
Zhi Yuanli from Suzhou University. Now I would like to ask reporters, the team of reporters, to introduce themselves.
Our team is 3. My name is Pen. He's Daniel. He's Jensen. He's Clyde.
Okay, thank you.
We are Team Mingdao Meiyan, and we are from Mingdao High School. And I'm the captain. I'm Roger. And this is Michael. And this is Alan. And this is Show. This is YC.
I am Sally Chen, and I'm from Aquarium Middle High School, and we are Team Excelsior. I'm the captain, and this is Alan, this is Robinson, this is Carlos, and this is Sandy.
Thank you. The opponent has 1 minute to propose a problem for the reporter. 1 minute.
So we would like to challenge problem number 3, lateral.
Accept.
Accept. So, problem number 1. Number 3. I'm sorry. Number 3. Okay. So please write down the names for each team's presenters. And with 5 minutes for the reporter to prepare. Okay, the reporter has 12 minutes to present his argument.
Hello everyone, my name is Pen for problem 3 lateral overview. The concept will contain how lateral start, how to convert a vertical force into a horizontal force, coefficient of restitution, small angle simple pendulum period formula. Problem statement. Attach a ball to each end of a string and connect the center of the string to a pivot. When the pivot oscillates along the vertical direction, the ball starts to collide and oscillate with increased amplitude. Investigate the phenomenon. Experience setup. We place the paper with a scale and with 5 centimeters to use tracker to analyze it, and pass the stickers to make sure the camera is in the same place, and make sure the camera and the wall is parallel and distance is 2 meters. Experiment method. We record the video to tracker to analyze it. We use tracker and Excel. And one ball is 7.7 gram. Another ball is 7.8 gram, and its radius is 1.5 centimeter, and length of the string is 20 centimeter. Concept. An initial speed is necessary to start lateral movement. Without that, the oscillation never begins. And with the initial speed, it can start. This is how vertical force turn to horizontal. This is from the perspective of force. This is tension of the rope. This is gravity. So it will be a horizontal component. And this is from the perspective of energy. This is gravity. And when it falls, it will be a velocity between 2 balls. MJ become half mv squared, and when it collide, will become half mv prime squared and become MJ prime. Concept. If it is elastic, and this is mass, and U1 and U2 is initial velocity, and V1 and V2 is final velocity. And if M1 equal M2, and then V1 equal U2, and V2 equal U1, and if U1 equal U2, then V1 equal U1. But in lateral case, it is inelastic, so U1 equal U2, and V1 equal EU1, and this E is coefficient of restitution. When this equals 1, and when it hit together, it will return to the same height. Concept. This is initial height, and this is final height. And this is final velocity, and this is initial velocity. This alpha is coefficient of restitution. MJ become half mv squared, and multiply alpha squared become half mv1 squared, become MJ prime. So H double prime, H prime equal alpha squared H. This is one impact, and H double prime equal alpha squared H prime equal alpha squared H. So this number, this 2 is number of impact. So it's like this. This small t is the time, and this big T is the period. And it comes from this small angle simple pendulum period formula. So it can get this, when it alignment, and this is fitting up, you will get this concept. This is simulation. When coefficient of restitution equals 0 to 1, it is inelastic, so it will be forced oscillation. As you can see, in the end, it's almost the same height. And this is simulation too. But when E equals 1, so it is elastic. But in theory, it might be the distinct bit note, but it is also forced oscillation. We think it might be the rope tension, the tension of the rope, and the rope may be slack. So a part of energy will turn to the heat. Data analysis. We use difference from high point and low point. And we can know how much energy that my hand input to lato-lato. Data analysis. When my lato-lato being a high space and my hand don't move, it will be decay. So you will get this line. This is exponential decay. This is theory. Our length of the string is 0.2 meters and gravity is 9.8. So period equals 0.89. But in practically, this 0.83 subtract 0.4 is 2 times in here. 0.4 and 0.83. And multiply 2 because and then this here and here is one period. But in lato-lato, it swung here and back to here. So you need to multiply 2. This is practical. And I can know two balls coefficient of restitution. It is 0.91 and 0.89. Conclusion. Initial speed is necessary to start lato-lato's movement. With the gap between two balls, the oscillation can start. Calculate the period using the small angle pendulum formula and derive the coefficient of restitution through the kinetic to potential energy equation. Estimated the energy input from the hand during stable oscillation and plotted a beating line.
The opponent has 2 minutes to question the reporter.
So first question, so you use hand to make the oscillation of the pivot.
Yes.
Is that true? Okay.
Yes.
And what do you mean by the ball needs initial speed to start?
My hand need to like
Yeah, I mean which direction of speed is needed?
my hand pull it and it can start with a gap.
Okay. So how do you measure the coefficient of restitution in reality?
I use the exponential decay alignment. This when I tidy it will get this, so I can get the coefficient of restitution.
So you have two simulations with
Yes.
different
with different.
coefficient of restitution, and what's the difference between these two simulations?
It is inelastic, and the other one is elastic.
Yeah, I mean, what's the difference in the results?
No difference because it all force oscillation.
Okay, and so okay, that's all my questions to ask.
Okay, the opponent has 3 minutes for preparation. Okay, the opponent has a maximum of 4 minutes to present his argument, followed by a discussion between the opponent and opponent for a total of 14 minutes. So please go ahead.
Okay, so this is opponent from Team Mindao Mei M, and today I will be opposing problem number 3, lateral. So here's the problem statement. And here is the overview of the reporter. So in the theory, they mentioned that initial velocity is needed to start the motion of lateral. And they consider the elastic collision and non-inelastic collision in the theory part. And also they mentioned about the coefficient of restitution. And lastly, they use the period of small angle pendulum equation to calculate the final results of the experiment. So, and their experiment, they do the experiment of changing and they do the experiment about the height of the lateral and the period. And the parameters will be the length of the line and the mass of the ball, and also the coefficient of restitution. And their conclusions is that as stated in the theory, lato needs initial velocity to start the motion. And also, they calculate the period with the formula they are using in the theory. And they also mention the energy transfer from the hand to the balls. And here's the pros and cons. So I think they have a very accurate simulation in their presentation, but my suggestion is that they should have more parameters, and in their theory part they could go further on the analysis. So here's the point I would like to discuss with the reporter. So in theory, I want to talk about the energy conservation you are using, and also the period formula of small angle. And in the experiment part, I would like to talk about how to control the oscillation of the pivots. And also, they calculated the coefficient of restitution, and I have some questions for that. So, we went to the proposal. So first of all, it stated that you use hand to control oscillation. So how do you know that the force you are applying and also the period of oscillation is the same in the experiment process?
As you can see, the picture, its period is almost the same, and its difference is almost the same too, and its standard deviation is so small. So I think it is the same.
Yeah, but this one is the oscillation condition of the ball, right? But I'm talking about the force you applied on the pivot. Yes, and so since the oscillation period of the pivot, maybe it doesn't match the oscillation period of the ball. So how can you ensure that they are the same?
You asked me. So sorry, can you speak again?
Yeah, may I use the block?
Sure.
So here's the system of the upper, right?
Yes.
So there you apply a force right here.
Yes.
So my question is that, so in this data you show the oscillation condition of the two balls, right? But I'm asking, how do you control this one? Since the oscillation period, maybe it doesn't match how you oscillate the pivot.
So ask me how I control that force.
Yes.
Just use hand. Then
So okay. So my suggestion is that maybe you can use maybe a machine to control the force applied on the pivot, so that all the control variable can be pretty much accurate in the experiment. Okay. So let's
but
move on.
you can see my standard deviation is so low.
Yeah, I mean, but this one is for the balls, and I'm asking the force on the field. But it's okay. Let's move on to the next question. So can I see your simulation part?
Simulation.
Yeah, this one. So in simulation, the coefficient of restitution is 1. That means no energy is lost during the collision, right?
Yes.
Then why does the ball has a maximum height that, as you show, it doesn't go up to.
Because the rope might slack or tension, so a part of energy will become heat.
So you consider slack in your simulation.
Yes, slack and tension.
Then how do you consider it? Like, do you have a
Okay.
formula for it?
Just see. Sorry. When it fall down, the rope will be shortened, and it symbolizes maybe slack.
Yeah, I mean, so the slack, since the slack condition is pretty complex, so is it actually possible for it to consider slack condition in simulation?
Yeah.
Yeah, I mean, slack condition is pretty complex, right? So you have to consider how much the string has been, so like how much time the string becomes slack, and the position won't be the same due to the slack of the string. So it's pretty difficult to consider the slack condition, right?
Slack condition just I fall down and will. It was slack. Yes, when I fall down it was slack, so I can know.
Okay, I get it. So can you move on to the part you talk about the calculation of the period? Back one. The concept. Back. With the formula. Yeah, this one. So the formula you're using, as we mentioned, is a small angle pendulum formula, right?
Yes.
But do you consider, since as you've shown in a demonstration video, the angle of the torso is way larger than the limitation of this equation. So do you correct this one?
I think it is accuracy because you can see this is use small angle pendulum like formula, and this is practically, and it's just 0.03 gap.
Yeah, but okay. Let me ask about another question. Is that what's the definition of your period? Since the lateral system is different than a single pendulum system. So what counts as a period?
What counts as a period? Here and here, like a pendulum.
So you mean when it goes back to the same place? Yes, but
it's like just one lateral and here. This is one period.
but the experiment we are doing is with two balls,
Yes.
right? So is the period you define is when the ball reaches its maximum height, and after collision, they went back to the same height. And
Two times.
yeah, that's why you call it a period.
Yes.
Yes, but since you calculate the coefficient of restitution, so and it's not equals to 1, so that means that it's a inelastic
Yes.
collision, right?
Yes.
So how come the ball goes back to the same height? Since there's energy loss, right?
Yes, it is energy loss.
Yeah. So from the energy conservation you are using, if I have an initial energy and after the collision, since my coefficient is not 1, so we lost energy, right?
Yes.
Then if we lost energy, the kinetic energy won't be enough for us to transform into potential energy, right?
So my hand input energy to this system.
Yeah, but since you can control your hand as you just mentioned, so I think the periods should have a more clear definition, and also okay. So can you turn to the conclusion part? Yeah. So as the problem statement stated, so investigate the increasing amplitude. So can you show me the parts that you investigate this one?
Sorry, we don't investigate.
Then what's your most important conclusion?
What's your conclusion? I think it is this.
So the point two. Yes. So can you explain from your experience data, like how does relevant parameters such as the
Sorry. What is
parameters, like the variable you are using, like something you change, like the length of string. So can you give a conclusion about that part?
So we don't make many variables, but we have simulation just e equals 1 and e equals 0 to 1.
Yeah, okay. So what's the variable you are using in your experiment? So can you turn to the page where you show the experiment data? The next one. So this is only a random variable. So what does this graph stand for? Shows.
Just I record video and use tracker to analyze it and get this back.
Yeah, and what's the conclusion of this graph? Yeah, I mean, what result does it show?
It shows the energy that my hand input in this system.
So do you calculate the energy you are putting in your hand?
Yes, it is 0.
Okay, we have to stop here. 1 minute summary time for the opponent.
So first of all, we talk about the experiment of the reporters. So I asked how do they make sure their force applied is always the same, and the reporter answers that the use handsaw is barely enough for them to control it, but they stated that the oscillation period of the ball is almost the same. So, but we don't think the oscillation period of the ball stands for the pivots. And next, we talk about the simulation of the reporters, and I asked why, if the coefficient is equal to 1, then why does the ball does not increase its amplitude furthermore? So the reporter answers that the simulation consider slack and other conditions, but I think it's not accurate since it's hard to consider the slack.
Now, the review has 3 minutes to present his argument.
Question to the reporter. Have small changes in initial ball position or velocity affected the long-term oscillation behavior? Since you mentioned in the report you will change the initial speed of the pivot, how will it affect the long-term oscillation behavior?
It can start oscillation. It can start oscillation.
And does that apparently influence to the experiment?
We don't measure it.
Okay. Does the opponent agree with that?
So you're asking what if the initial velocity is different, the result will be different or not, right?
Yes.
So I think since the coefficient of restitution is maybe it's not fixed, so yes, the initial condition might actually affect the the stable condition finally.
Okay, thank you. I get your point. And question for the opponent: how does the non-sine wave pivot oscillation affect the both collision frequency and amplitude growth? Since you have mentioned the pivot acceleration during the discussion, what do you think the pivot acceleration will affect to the experiment?
We believe that when the oscillation period of the pivot can matches the oscillation period of the both, it goes to a steady condition.
So
A
you
steady
will have
condition.
the increasing amplitude.
Yeah, I mean, maybe the initial amplitude is small, but after the accumulation of energy, it will reaches a stable condition where the amplitude stays the same.
Okay, thank you. And does the reporter agree with that?
You say when measure period, it will be
Short answer, please. Yes or no? Do you agree with the opponent?
Yes.
Okay, thank you. And question for the reporters: does changing the pivot oscillation frequency or amplitude cause unstable behavior?
Yes.
Okay. Does the opponent agree with that?
It depends.
It depends. What do you mean? Can you further explain?
So, as I just mentioned, under certain conditions, the oscillation frequency of the pivots can match the oscillation frequency of the ball.
Okay, thank you. And question for the reporters: to what extent of frequency will balls start to have an irregular collision?
Period. 0.43.
So you have a specific boundary limits for the experiment.
Yes.
Okay, thank you. And question for the opponent: will the change in tension of the rope affect the collision frequency of the ball?
The tension of what?
Of the tension of the string, change the amplitude of the lateral.
Okay, 3 minutes for review of the path.
The reviewer would like to skip the time. Honorable juries and fellow competitors, I'm the reviewer from Team Self here. Today, I'm going to review problem number 3, lateral. This is a problem statement, and we will mainly focus on how does the mechanism behind the increasing amplitude affect the phenomenon, and what parameters will affect the amplitude of oscillation. First, let's talk about the review of the report. The reporter has observed the phenomenon in which the balls start to collide and oscillate with an increasing amplitude. And the theory the reporter mainly used is a force analysis to calculate the energy transformation during about the two lateral spots. And the energy transfer between the potential energy and the kinetic energy is the main theory that the reporter used in his experiments to describe the motion patterns of the lateral. And about the experiment, the reporter has done the mass of the balls However, that's only the slightly change of the parameters and also the length of the pendulum. And the reporter has shown the simulations to describe how different elastic coefficients affect the phenomenon. And now let's talk about the strong and weak points for the reporters. The reporter did a good job in providing a demonstrative phenomenon and explained the cause of the phenomenon well, and provided a very clear observation video. However, there is lack of comparative experiments under different conditions to verify the influencing factors to the experiments. And there is lack of fear and rely. And the reporter didn't explain why certain variables influence the results, and didn't provide the device that can control the pivots, since that's only the manual conductment to the experiments. And there is lack of the parameters then corresponding to the first point. And however, it provides a very clear explanation of the phenomenon. Now let's talk about the review of the opponents. The opponents did a great job and noticed the lack of explanation for deviation, and noticed the lack of parameters and experiments, and further discussed this with the reporter. And notice the reporter didn't explain the physics behind the phenomenon, so the opponents asked the reporter to say the further information about the phenomenon behind the physics behind the phenomenon, and made a well-intended suggestion to the reporters. However, in the discussion time, they didn't discuss the boundary conditions in laterals, which is the boundary limits of the amplitude. And this didn't discuss the deviation might caused by the manual conductment experiments, and didn't notice the lack of explanation behind the deviations. And he failed to notice the lack of an arbitrary line, which may result in a big misunderstanding in the experimental results. Now let's talk about their key discussion. The control of the pivots is one of the main discussions they have talked about. The opponents asked the reporter how to control the oscillation period applied on the pivots. The reporter said, "I use my hand." The reviewer thinks that it's one of the influencing factors to the experiments. We agree with the opponents. It needs to be controlled by the machine to minimize the deviations. And the second key discussion is energy conservation. The opponents asked how to consider the state or tension in the experiments. The reporter said we consider the state. However, we suggest the reporter can do further experiments to ensure the stability of the lens during collision. And this is our first question. Has small change in initial position and velocity affect the experiments? The reporter said it can start oscillation, but we don't measure it. The opponent thinks that the initial speed might affect the stable condition. And about the appointments, the lack of discussion on parameters, which is elasticity of the raw materials, and energy conversion process, overlook the energy dissipation from ball collision as the heat of sound, and method of the experiment did not consider the pivot's oscillation effects. And that's the end of the review. Thank you.
Okay. 2 minutes summary time for the reporter.
Today we talk about variables, and I don't do so many experiments, and is my hand accurate, and with a small angle pendulum formula. Okay, our experiment using tracker to analyze the position and the height of the apparatus. Data, coefficient of restitution, energy divided by 10. The conclusion, the gap between two balls and the elastic speed is the point to make the equipment move, and the coefficient of restitution. What kind of variable you use in this experiment? We only focus on the specific equipment. How to control the force handling with the data shot and the standard deviation. That's accurate, I think.
Question time from viewers. I have a question. So what's the purpose to do this simulation? Because we are expecting that when you have a simulation, you should compare with your experimental data.
Let's look at next relation is just to tell when it E equals 1 or equals 0 to 1, it both are forced oscillation.
So you didn't.
Well, I didn't.
Because you have a code, right? You can change the variable on the parameter, right? So did you try to do this kind of test and compare with the scale?
So I have one question for all of you. Okay, so first for the part. So actually they are the same question. The question is that you mentioned that the amplitude is an important parameter, the pattern, right? So how about if you change the frequency? You keep changing amplitude, but how about the frequency? If you change the frequency, it will affect the whole phenomenon.
I mean the frequency of the pivots.
Yes.
So I think the frequency of the, so I said if the lato needs to get into a stable condition, the oscillation frequency of the pivots is required to be the same as the oscillation frequency of the ball. So if the frequency of the pivot keeps changing, I think the ball will never reach a stable condition.
We think the acceleration of the pivots is one of the very influencing factors to the experiment. Like when we change the frequency of the pivots, it will attend to a stable condition, which can the lato have a stable collision. And however, it can do the further experiments on the boundary condition. When the pivot is over a certain frequency, the collision will become unstable, like the opponent has mentioned.
Yes, it will be unpredictable because you need to match the to multiply natural frequency, and that is stable.
Any questions? One more question for the viewer. In your presentation, you mentioned about the boundary condition of the collision, right? So what do you mean by the boundary condition?
Well, the boundary condition can be considered in many perspectives. Like in pivot's perspective, when the pivot is over a certain kind of frequency, the lato will have an unstable collision. And another boundary condition will be the amplitude of the lato. Like since the lato have a very popular method to play, which is the up and down collision. The lato ball can have an up-down collision. So we think that's one of the very interesting phenomena they can consider as a boundary limit, which is the maximum amplitude of the lato.
So how to control this condition?
Well,
How do you think of that?
To control a small collision of the lato, it can be adjusting by the method of like stagger motor to control the timing belts to drive the pivots, and it can make the lato to climb. However, the up and down collision, the reviewer just mentioned, we think that's kind of hard for the machine to do that kind of phenomenon. So we think up and down collision maybe just can be done by the manual conduct experiment.
Any more questions? Okay, thank you. Yours. Okay for the short slide. Okay. For the reporter, have 5, 4, 4, 4, and 7 for the opponent. And 7, 6, 7, 6, and 8. And for the reviewer, 7, 7, 8, 7, and 9. Okay. Okay. This is the end of our first part of afternoon session. So we'll take a 10 minutes. Well, 10 minutes. Okay. 10 minutes. We have a 10-minute break. Is that okay for you guys? Okay, we'll have 10 minutes break.